Welcome back to Slumbering Myths. Find a comfortable position. Lay on your back, relax your shoulders, and take a very slow, very long breath. Tonight, we will not travel far. We only need to look up, high above, to the place where light and darkness meet. Imagine you are standing on an empty hill. A gentle breeze blows past your shoulders. The sky above you is a crystal clear blue, without a single cloud. And then, everything begins to change. Very slowly, very subtly, as if someone is gradually turning down a giant lamp of your head. The birds stop singing. The air becomes strange, cooler, softer, like early morning even though it is the middle of the day. The flowers in the field close their petals, and the stars begin to appear. In the middle of the day, you look up and you see it. A silvery white halo, shimmering ethereal, surrounding an absolute dark void suspended in the sky. That is the solar corona. That is the true face of the sun. A face that normally its own blinding light hides from us every single day. And you only have a few minutes. A few brief minutes to look into the greatest mystery of our closest star. In the year 2026, that moment will happen. A total solar eclipse will sweep across the Arctic, stretch down to Spain, cross North Africa. And millions of people on Earth will look up at the exact same time, holding their breath together, seeing the very thing our ancestors once feared, once worshipped, once called an omen of the gods. But tonight, we will not just look. We will understand. We will go inside that halo of light, into the hottest, most chaotic, and most miraculous layer of atmosphere in the entire solar system. We will touch the strands of plasma winding like giant serpents along the magnetic field lines. We will ride the solar wind, a stream of charged particles flowing at millions of kilometers per hour, shooting straight out into space. And we will stand before a question that the greatest physicists in the world have still not answered after more than 70 years of research. Let us begin. The sun that you see every day, the blinding yellow glowing orb in the sky, is actually just its surface. Or more accurately, it is the outermost layer of the part our eyes can see. Scientists call it the photosphere. This is where light is born, where the temperature is about 5,500 degrees Celsius, hot enough to vaporize any metal ever found on Earth. That sounds incredibly hot already, doesn't it? But outside that layer, there is something else. Imagine you step away from the surface of the sun, which is burning at thousands of degrees, and you continue to move further away, higher up, into the space surrounding the sun. You would think things must get colder, right? Just like when you step away from a fire, the air gradually cools down. But no. The further away you go, the hotter everything becomes. Not just a little bit, but a discrepancy that made scientists fall backward when they first discovered it. The outermost atmospheric layer of the sun, known as the solar corona, has a temperature ranging from 1 million to 3 million degrees Celsius. Sometimes, in particularly active regions, the temperature can reach 10 million degrees. The surface, 5,500 degrees. The corona, 3 million degrees. You move away from the heat source, and everything gets 500 times hotter. This is one of the greatest physical paradoxes that modern science has not adequately explained. Scientists call it the coronal heating problem, and it has existed as an unsolved puzzle for over 7 decades. The corona exists right around the sun, stretching out for millions of kilometers into space. But you have never seen it with your naked eye on a normal day. The reason is very simple, but also very fascinating. The surface of the sun, the photosphere, is about 1 million times brighter than the corona. It is as if you are trying to see a flickering candle while standing in the middle of the Sahara Desert at high noon. The blinding light of the surface completely drowns out, obscures, and swallows the faint light of the corona. Scientists invented a device called a coronagraph, a special telescope with a circular disc that blocks the direct light from the sun, to observe the corona at any time. But even the most modern equipment cannot recreate the clarity, the detail, and the magnificence that we see during the 2 minutes of a total solar eclipse. Because during a total eclipse, the moon does something no technology can do. It perfectly obscures the surface of the sun in a bizarre way. Nothing more, nothing less. This is something few people notice, but once you hear it, you will never forget it. The sun is 400 times larger than the moon. And the sun is also 400 times further away from us than the moon. Those two numbers, coincidentally, completely cancel each other out. The result is, looking from Earth, the sun and the moon have the exact same apparent size in the sky. This is not the design of anyone. This is a cosmic accident, a coincidence so profound that if you were on any other planet in the solar system, you would never witness this. And that exact perfect coincidence creates a total solar eclipse. The moment the moon completely covers the surface of the sun, not revealing a single tiny sliver, but also not hiding the brilliant corona outside. Like a ring of light. Like an eye looking down from the heavens. Like a portal opening to a world that is normally hidden from us. Thousands of years ago, when an eclipse occurred, humans did not understand what was happening. They only saw the sky darken and a mysterious ring of light appear. Ancient Chinese people believed that a dragon was swallowing the sun. They beat drums, shouted, and shot arrows into the sky to chase the dragon away. The Vikings thought it was two cosmic wolves, Skell and Hati, hunting down and catching the sun. The Incas knelt down, prayed, and offered sacrifices. But within all those fears and myths, a truth was hidden inside. That ring of light is real. It is not a hallucination. It is not magic. It is what truly surrounds our sun every single day, silently, majestically, and full of mystery. It was not until the year 1869, during a total eclipse observed in America, that scientists first used a spectroscope to analyze the light of the corona. And they discovered a yellow-green spectral line, a line that did not match any known element on Earth at that time. They named that mysterious element helium, derived from Helios, the sun god in Greek mythology. 27 years later, helium was finally found on Earth. That was the first time in history humanity discovered a chemical element not on Earth, but on the sun through the light of the solar corona. And we return to the biggest question. Why is the corona hundreds, thousands of times hotter than the surface of the sun? In terms of basic thermodynamics, you cannot receive more heat from a place that has lower heat. Heat always transfers from hot to cold, never the other way around. So what is pumping energy into the corona? Currently, there are two major theoretical schools of thought competing in astrophysics. The first school believes it is alpha waves. Incredibly powerful magnetic waves propagating along the magnetic field lines, carrying energy from the surface up to the corona and releasing that energy as heat. The second school believes in nanoflares. Millions of tiny explosions occurring constantly, each one too small to be observed directly, but combined they create enough energy to maintain the million-degree temperature of the corona. Both theories have supporting evidence. Both theories fail to completely explain everything. And that is exactly why the 2026 eclipse is so important. In those rare moments when the sky darkens in the middle of the day, scientists around the world will point their best telescopes at the solar corona, hoping to gather enough data to finally, after more than 70 years, provide an answer. And we will wait for that moment. Together. Since childhood, we are taught that matter exists in three states: solid, liquid, and gas. Ice, water, and steam. Simple, easy to understand, and neat. But there is one thing that most standard textbooks do not tell you. The most common state of matter in the entire observable universe is not solid, not liquid, and not gas. It is plasma. And over 99% of visible matter in the universe, all the stars, all the nebulas, all the giant gas clouds between galaxies, exist in the form of plasma. So, what exactly is plasma? Let us start with the atom. A normal atom has a nucleus in the center, carrying a positive charge, and electrons orbiting around it, carrying a negative charge. Normally, these two parts balance each other out, making the atom electrically neutral. But when you provide enough energy, enough heat, enough pressure, those electrons are ripped away from their orbits. They escape and become free. And you are left with a chaotic mixture of positive nuclei and negative electrons, unbound to each other, flying freely, colliding and reacting. That is plasma. It is not a gas, because a gas is made of neutral atoms or molecules. Plasma is an electrified gas, a completely different state, with completely different properties. And the most important property of plasma is this. Plasma reacts to magnetic fields. Powerfully, dramatically, and sometimes completely out of control. The entire sun is made of plasma. From the core, where temperatures reach 15 million degrees Celsius and nuclear fusion burns millions of tons of hydrogen every second, all the way to the outermost corona that we just talked about. But not all plasma is the same. At different depths, in different regions of the sun, plasma has different densities, different temperatures, and most importantly, it moves in different ways. And it is exactly that movement that creates the very thing that shapes the entire story we are telling tonight. The solar magnetic field. The Earth has a magnetic field. You know this. It is why compasses work, why migrating birds can find their way, why we are protected from dangerous charged particles from the solar wind. But the magnetic field of the sun is nothing like the magnetic field of the Earth. Not at all. The Earth's magnetic field is quite stable, quite simple, like a giant magnet with relatively fixed north and south poles. The sun's magnetic field is chaotic, dynamic, and sometimes completely insane. The reason is because the sun does not rotate evenly like the Earth. The Earth rotates as a solid body. Every point on its surface turns at the same speed. But the sun is plasma, it has no solid surface, and different regions rotate at different speeds. The equator of the sun completes one rotation in about 25 days. But the polar regions take up to 35 days to complete a single turn. Imagine this happening to a piece of rope. If you hold both ends tightly and twist them at different speeds, the rope will begin to twist, knot, and stretch tight. The exact same thing happens to the magnetic field lines of the sun. They are pulled, twisted, wrung out, and bent. Over weeks, over months, the initially simple magnetic lines become a dizzyingly complex network, intertwining, stretched to their absolute limits. And when that tension crosses a certain threshold, everything bursts. But before they burst, let me tell you about the things they create. Because it is precisely from that twisting that the most miraculous structures in the solar system are formed. Scientists call them magnetic filaments or solar filaments. These are giant ribbons of plasma, hundreds of thousands of kilometers long, trapped and shaped by magnetic field lines, curving like massive arches above the solar surface. Visualize it like this. You take a magnetic wire and bend it into an arch, planting one end into a region on the sun's surface, and the other end into a different region, tens of thousands of kilometers away. Along that invisible wire, plasma is drawn in, trapped, and shaped, forming a long and thin structure. It is darker and cooler than the surrounding area, suspended above the solar surface like mysterious clouds. Viewed from above by a solar observation satellite, they look like dark, zigzagging strands of hair stretching across the face of the sun. Viewed from the side, from the edge of the sun, they flare up into giant, brilliant, majestic rings of fire, reaching out into space for tens to hundreds of thousands of kilometers. When we see them like that, we call them solar prominences. Solar prominences are one of the most magnificent sights you can observe in the entire solar system. They are colossal loops of plasma, fiery, twisting, dancing, clinging to the magnetic field lines and reaching far beyond the solar surface. To give you a sense of their true scale, an average solar prominence can be 10 to 20 times taller than our Earth. Not taller than a building, not taller than a mountain, taller than our entire planet. 10 times, 20 times over. And they endure for days, for weeks. Some exceptionally stable prominences can last for months before slowly fading away or suddenly erupting. Erupting, that is the key word. Because when a solar prominence becomes unstable, when the magnetic thread holding it snaps or abruptly reconnects, it does not simply disappear. It launches into space. Billions of tons of plasma, burning at millions of degrees, are shot straight into the cosmos at millions of kilometers per hour. We call that a coronal mass ejection, or CME for short. And if that trajectory is aimed directly at Earth, we will talk about that later. But prominences are not the only structures created by the Sun's magnetic field. Let us talk about something the ancients also saw and did not understand why. Sunspots. If you look at the surface of the Sun through a telescope with a proper filter, of course, never look directly at the Sun, you will see darker regions, like bruises on the skin. Galileo observed them in the 17th century. The Chinese recorded them over 2,000 years ago. But it was not until the 20th century that we understood what they truly are. Sunspots are regions where the magnetic field is incredibly strong. Thousands of times stronger than the average magnetic field of the Sun, piercing through the surface and suppressing the convection of plasma. Normally, hot plasma from the inside continuously bubbles up to the surface, like boiling water in a pot, carrying heat and making the surface glow brightly. But in those regions of extreme magnetic strength, that convective movement is blocked. The plasma cannot bubble up. As a result, that specific area becomes colder, only about 3,500 degrees Celsius instead of 5,500. And colder means darker. That is a sunspot. They usually appear in pairs or in groups, where the magnetic field lines enter and exit the solar surface, like the two poles of a giant magnet hidden beneath. And between two sunspots in the same group, stretching the magnetic lines between them, massive loops of plasma constantly form, grow, and sometimes erupt. Now let us talk about the most dramatic part. Imagine you are stretching a rubber band. The more you pull, the tighter it gets, energy steadily building up inside. And then you let go. All that energy is released in a fraction of a second. The exact same thing happens to the magnetic field lines of the Sun when they are twisted and stretched too far. At a certain point, two magnetic lines carrying opposite polarities come into contact with each other. And what happens next is called magnetic reconnection. This is one of the most energetic physical phenomena that we know of. In an instant, literally within seconds or minutes, the magnetic energy accumulated over hours and days is completely released. The result is a solar flare. An incredibly intense flash of light, millions of times more powerful than a nuclear bomb, shooting out from the surface of the Sun, carrying X-rays and ultraviolet radiation with an intensity that can impact the Earth's ionosphere in just 8 minutes, traveling at the speed of light. And accompanying that flare, or sometimes separate from it, is the CME, the coronal mass ejection I mentioned earlier. Billions of tons of plasma are blasted out, moving at speeds of 500 to 3,000 kilometers per second. If it is heading toward Earth, it will arrive within 1 to 3 days. And this is where our story gets truly fascinating. Because, until recently, we observed all of these things from afar. From Earth, from satellites at a safe distance. But in 2018, NASA launched something unprecedented in the history of science. The Parker Solar Probe, a spacecraft designed to fly directly into the corona of the Sun. Not observing from afar, not measuring indirectly, but flying straight in. This was an almost unimaginable engineering challenge. At the closest distance to the Sun that Parker reaches, the environmental temperature outside the spacecraft hits nearly 1,400 degrees Celsius. But inside the ship, protected by a special carbon heat shield nearly 12 centimeters thick, the temperature is only about 29 degrees Celsius. As cool as a spring day, just a few centimeters away from the heat shield. Parker has flown through the corona multiple times, and what it sent back has completely changed how we understand the Sun. It discovered incredibly powerful waves of plasma, known as switchbacks, magnetic structures that abruptly bend and reverse direction, carrying massive energy and possibly holding a piece of the answer to the coronal heating problem. It measured the solar wind right at its source, before it was diluted and scattered out into space, giving us unprecedented data on the acceleration mechanism of this stream of charged particles. And most importantly, it showed us that the corona is uneven, unstable, and far more complex than any theoretical model we ever had. But no matter how advanced the Parker Solar Probe is, it can only measure what it passes through. Like a small boat cutting across the ocean, it tells you everything about the water along its path, but it cannot tell you what the entire ocean looks like. To observe the entire corona, its three-dimensional structure, the distribution of plasma within it, the shape and dynamics of every single filament, you need to look from the outside. And the best way is still to stand on Earth and wait for the moon to do its job. During the 2026 total solar eclipse, scientists will deploy networks of telescopes along the entire path of totality, from Greenland down to Spain and into North Africa. They will observe the corona with high-resolution spectroscopy, tracking the movement of every plasma structure, measuring the magnetic field directly from the light of the corona. And this time, they have an advantage that previous generations did not have. The year 2026 falls exactly during the solar maximum, the period when the Sun's activity reaches its peak. The magnetic field is at its strongest, the number of sunspots is highest, and solar flares appear most frequently. The corona during the solar maximum looks completely different from the corona during a quiet period. It is more complex, more dynamic, and holds even more mysteries to uncover. Are you feeling it? The realization that the Sun, the thing we see every day, the thing we thought we knew so well, is actually hiding secrets far greater than we imagined. Giant plasma filaments twisting and turning. Magnetic loops stretching to their breaking points. Explosions carrying the energy of millions of nuclear bombs happening right now, right as you are listening. And all of those things are firing straight toward us. But wait, what happens when they arrive? What does the solar wind, that massive stream of charged particles, do when it touches the Earth? That is what we will explore in the next chapter. Right at this very moment, while you are lying down, breathing steadily and listening to this voice, there is an invisible current blowing right through you. Not the wind you feel on your skin, not the air slipping through your window, but a stream of millions of charged particles, fragments of atoms, moving at speeds of hundreds of kilometers per second, piercing through you, through the room where you lie, through the entire Earth, as if we do not even exist. That is the solar wind. And it has been blowing relentlessly since before the Earth was formed, since before life appeared, since before the first human looked up at the sky and wondered where that light came from. For billions of years. Continuous, invisible, and powerful enough to shape the entire solar system. In the year 1958, an American astrophysicist named Eugene Parker published a scientific paper. In it, he proposed an idea that most of his colleagues considered insane. He stated that the Sun is constantly blowing out a stream of matter, of plasma, into space in all directions. That this flow never stops. That it fills the entire solar system like an eternal, invisible wind. The scientists of his time rejected him. Scientific journals refused to publish his paper. They said that space is a vacuum, completely empty, and nothing could travel through it in the way he described. But Eugene Parker did not back down. And 4 years later, in 1962, the Mariner 2 probe, on its way to Venus, directly recorded this continuous stream of charged particles from the Sun for the very first time in history. Eugene Parker was right. And 60 years later, in 2018, NASA named the spacecraft flying into the solar corona after him, the Parker Solar Probe. This was the first time in history NASA named a spacecraft after a living scientist. And Eugene Parker, who was 91 years old at the time, was present at the launch pad to witness the ship bearing his name leave the Earth. Now we know the solar wind is real. But where does it come from? How is it created? The answer lies in the corona, the outermost atmospheric layer we just talked about. Remember this, the corona has a temperature of millions of degrees. At that temperature, plasma particles move at incredibly high speeds. So high that some of them reach the escape velocity needed to break free from the Sun's gravity. Think about it like this. You boil a pot of water. The fastest moving water molecules, the ones with enough energy to escape the surface, rise up as steam. The exact same thing happens with the corona. The plasma particles with enough energy, protons, electrons, and some heavier nuclei like helium, escape the Sun's gravitational pull and shoot out into space. Relentlessly from all directions, at all times. But not every place on the corona releases the solar wind at the same speed or the same density. And this is where we encounter another structure, a structure that scientists have only truly understood in recent decades. Looking at the surface of the Sun through X-ray or ultraviolet wavelengths. Wavelengths that satellites can see but the human eye cannot. You will see something strange. Large, irregular dark regions spreading across the solar surface. Not sunspots, which are much smaller and more defined, but vast dark expanses, sometimes taking up to a quarter of the Sun's surface area. Those are coronal holes. And they are the gateways, the places where the solar wind blasts out the strongest, the fastest, and the most fiercely. The reason is this. In most regions on the Sun, the magnetic field lines form arches. Starting from one point on the surface, reaching up into the corona, and then curving back down to end at another point on the surface. Like magnetic rainbows. Plasma is trapped within those arches, imprisoned, unable to escape. But at a coronal hole, the magnetic field does not form an arch. It opens up. Like doors being flung wide open, the magnetic field lines shoot straight out into space. Never curving back, never closing, extending infinitely into the solar system. And along those open magnetic lines, plasma escapes freely. The fast solar wind, reaching speeds of up to 800 kilometers per second, spews from these coronal holes like a giant faucet turned on full blast. Compared to the solar wind from other regions, which is slower, around 400 kilometers per second, the wind from coronal holes is twice as fast. And when those two winds meet, when the fast stream catches up to the slow stream, they collide, creating high-pressure regions, shock waves, and complex structures stretching for millions of kilometers in interplanetary space. Let us follow a single proton, a tiny fragment of the solar wind, on its journey from the corona to the Earth. It begins in the corona, where the temperature of millions of degrees gives it enough energy to escape the Sun's gravity. It is launched outward along an open magnetic field line or simply blasted out in a small coronal explosion. In the first few hours, it accelerates, pushed further by the pressure of the corona and the release of magnetic energy. Then it continues its journey through the empty space between the Sun and the planets. Nothing stops it. There is no friction. There is no resistance. Only darkness and the vast void. And after about 3 to 4 days, sometimes faster if the wind is strong, it arrives. It approaches the Earth. But the Earth is not helpless against it. The Earth has a protector. an invisible shield surrounding our planet. Unseen, untouchable, but it has protected life on Earth for billions of years. That is the magnetosphere, the region of space influenced by the Earth's magnetic field. When the solar wind approaches the Earth, it collides with the magnetosphere. And what happens next is one of the most miraculous physical dances in the solar system. On the side facing the Sun, the day side of the Earth, the magnetosphere is compressed, pushed down like a punched pillow. Normally it extends about 65,000 kilometers toward the Sun. When the solar wind is strong, it can be squeezed down to 40,000 kilometers or even less. On the backside, the night side of the Earth, the magnetosphere is stretched out, elongated into a giant tail extending millions of kilometers behind us, like the tail of a comet. Most of the solar wind particles are deflected, sliding along the surface of the magnetosphere, redirected, pushed away, unable to penetrate inside. But not all of them. At the two poles of the Earth, the North Pole and the South Pole, the magnetic field lines point straight down into the ground. And right there, a small door opens. Those solar wind particles, protons and electrons, follow along those magnetic lines, slipping down into the Earth's atmosphere. At an altitude of about 100 to 300 kilometers, in the ionosphere, they collide with atmospheric molecules. Oxygen, nitrogen, the tiny elements that make up the air we breathe. Every collision is a transfer of energy. Every molecule excited by that energy will emit light when it returns to its normal state. And that light, millions and billions of molecules glowing all at once, is what people in the polar regions see in the night sky. The aurora. Aurora borealis in the north. Aurora australis in the south. Green, from oxygen at lower altitudes. Red, from oxygen at higher altitudes. Purple and blue from nitrogen. Giant curtains of light dancing across the night sky. Not magic, not myths, but visible proof that the solar wind is touching us. Right now. Every night. Relentlessly. But the solar wind is not always gentle. Remember the CME, the coronal mass ejection, that we talked about in the previous part. When a CME is aimed directly at the Earth, what happens next is no longer just a wind. It is a storm. A geomagnetic storm occurs when a CME collides with the Earth's magnetosphere, temporarily disrupting its balance, pushing high-energy particles much deeper into the atmosphere than normal. During massive magnetic storms, auroras can be seen at unusually low latitudes. Not just in Norway or Alaska, but in France, in Japan, even in Mexico. That is the beauty of a geomagnetic storm. But there is another side to it. A side that we, a modern civilization entirely dependent on electricity and technology, need to seriously worry about. The year 1859. The night of September 1st. The largest geomagnetic storm ever recorded in human history struck the Earth. Astronomers call it the Carrington event, named after astronomer Richard Carrington, who observed and recorded the massive solar flare that caused it one day prior. Auroras appeared all over the world. In Cuba, in Hawaii, in the tropics of Central America. Some people in the southern United States woke up in the middle of the night, thinking it was already morning. Miners in the Rocky Mountains woke up and started cooking breakfast because they thought dawn had arrived. But the real consequence was not the beautiful light. The entire telegraph network, the most advanced communication technology of that era, completely collapsed. Telegraph wires sparked with fire. Telegraph machines operated on their own without a power source, running entirely on the induced current from the geomagnetic storm. Some telegraph stations caught on fire. And that was in 1859, when humanity's technology consisted only of telegraph wires. Now think about the world in 2026. The GPS satellites you use to navigate. The national power grids supplying electricity to entire countries. the global internet network, the communication systems of airplanes and ships, the servers of banks, hospitals, and stock exchanges. A Carrington event happening today would not just burn telegraph wires. Studies estimate the damages could reach trillions of dollars, and the recovery process could take years. This is not science fiction. This is astrophysics. And this is why space weather forecasting is a scientific field receiving increasingly serious investment. And here is what I want you to take with you as we conclude this part. The solar wind is not something separate from the corona. A CME is not something separate from the solar magnetic field. A geomagnetic storm is not something separate from what happens on the surface of the sun. They are all one continuous system. From the core of the sun, where nuclear fusion creates energy, to the surface, where that energy boils and twists the magnetic field, to the corona, where that magnetic field heats the plasma to millions of degrees and launches the solar wind outward, to interplanetary space, where that wind spreads, accelerates, and collides, to the Earth's magnetosphere, where our magnetic field confronts and guides that flow, to the ionosphere, where the lucky particles that slip through create the light show that humans have gazed upon and worshipped for thousands of years. And when we understand that system, when we can forecast it just like forecasting the weather, when we know 3 days in advance that a storm is going to strike, we can intentionally turn off satellites to protect them. We can secure the power grids. We can warn the crew on the International Space Station to take shelter in safe zones. Understanding is protection. And the 2026 eclipse, by allowing us a clearer look into the corona, into the birthplace of the solar wind, is a small but crucial step in that journey. Have you felt the wind yet? Not the wind outside your window, but that invisible breeze blowing through you right at this moment, connecting you in the most literal sense of the word to the brightest star in the sky. We are not separate from the sun. We are living inside its outermost atmosphere, protected, nourished, and sometimes challenged by its continuous breath. And in the year 2026, when the shadow of the moon falls and the corona blazes across the sky, scientists will try to understand just a little bit more about our giant and mysterious companion. We will explore that together in the next part. There are days that scientists know about centuries in advance. Not through prophecy, not through intuition, but through mathematics. Because the movements of celestial bodies, the sun, the moon, the earth, follow physical laws so precise that we can calculate, down to the second, when and where the darkness will fall. And that day is August 12th, 2026. This is the day when the moon, in its familiar orbital journey around the Earth, will move into an absolutely perfect position. Not a fraction too far north, not a fraction too far south, but directly, accurate to the kilometer, onto the straight line connecting the Earth and the Sun. And its shadow will draw a long curve across the surface of the Earth. A narrow corridor, about a few hundred kilometers wide, where those lucky enough to stand within it will witness the moment the entire solar system seems to hold its breath. Let us follow that shadow from the moment it touches down on Earth until it disappears. It begins in the Arctic, on the freezing ice of the Arctic Ocean, where almost no one lives. The darkness sweeps across the white expanse of ice and snow, with no witnesses other than polar bears and silently drifting icebergs. Then it continues moving south, faster than you think, at a speed of over 2,000 kilometers per hour. Crossing over Greenland, casting its shadow upon the majestic ice mountains and deep fjords of the world's largest island. From Greenland, the shadow crosses the Atlantic Ocean. And then it touches the continent. Spain, the land of wine and golden sunshine, will be the first place in Europe to receive the total solar eclipse. The corridor of darkness will pass through Bilbao, Zaragoza, Valencia. Major cities where millions of people will pour into the streets. Look up at the sky and stand together in silence for the most precious few minutes of that year. From Spain, the shadow crosses the Balearic Islands, Mallorca, Ibiza, then across the Mediterranean Sea. And the final stop on land is North Africa, Algeria, Tunisia, Libya. Before the shadow finally leaves the surface of the earth and dissolves into the darkness of space. The entire journey of the shadow from touchdown to departure takes only about an hour and a half. But at any given point along that path, the moment of totality, when the moon completely obscures the sun, lasts only from 2 to 7 minutes. No more. A total solar eclipse occurs on average about once every 18 months somewhere on Earth. So what makes the 2026 eclipse so special that scientists are already planning for it now? There are 3 reasons. And each reason, on its own, is enough to excite the astronomical community. When all 3 happen at once, it is something that cannot be missed. The first reason, an unusually long duration of totality. The time the corona is completely revealed, called totality, depends on the relative distance of the moon to the Earth at that moment. The moon's orbit around the Earth is not a perfect circle, but an ellipse. When the moon is at its closest point, perigee, it appears slightly larger and covers more, extending the duration of totality. The August 2026 eclipse occurs when the moon is near perigee, meaning that at certain points along the corridor, totality could last for nearly 7 minutes. This is one of the longest eclipses in many decades. 7 minutes. It might seem short to you, but to an astronomer who has waited years, flown halfway across the globe, and brought tons of equipment, 7 minutes is priceless. The second reason, the corridor passes through densely populated areas. Not every eclipse politely passes over major cities. Many eclipses pass over oceans, over deserts, over polar regions, places where only the most determined scientists can pursue them. But the 2026 eclipse goes through the heart of Spain. One of the countries with the best infrastructure in Europe, with a dry Mediterranean climate in August, much less cloudy than other regions. That means equipment is easy to transport, electricity is available, communication networks are stable, and most importantly, clear skies with a high probability. For a scientist, bad weather can destroy a lifetime of preparation in minutes. Spain in August is one of the safest meteorological bets. The third reason, and this is the most important one, the solar maximum when the sun is at the peak of its fury. The sun is not always the same. It has a cycle, an 11-year rhythm where its activity rises and falls, strengthens and weakens, boils and quiets down. During the solar minimum, the sun is quite calm. Few sunspots, few flares, few CMEs. The corona looks simple and symmetrical, mostly just 2 faint plumes at the poles. But during the solar maximum, the sun becomes active, chaotic, and miraculously unimaginable. Sunspots appear everywhere. Flares erupt frequently. CMS launch continuously. And the corona, instead of being simple and symmetrical, becomes a complex network of giant plasma loops. Filaments stretching millions of kilometers. Magnetic structures endlessly twisting and exploding. The corona during the maximum looks completely different from the corona during the minimum. It is more brilliant, more complex, and holds more mysteries to explore. The current solar cycle, cycle 25, is heading toward its maximum around the years 2025 to 2026. And according to many forecasting models, cycle 25 is stronger than initially predicted. Much stronger than the previous cycle, which was one of the weakest in the 20th century. Meaning that when the eclipse occurs in August 2026, the sun might be at the very peak of its activity. The corona will not just be revealed. It will be ablaze. This is a combination that astronomers will not see again for many years, even decades, to come. Scientists around the world are not sitting and waiting. Right now, as you are listening, plans are being drawn up. Equipment is being built. Computational models are being tested and refined. All in preparation for those 7 minutes. A network of telescopes along the eclipse corridor. A single telescope can only observe for 7 minutes, the time of totality at one point. But if you place multiple telescopes along the entire corridor, spaced hundreds of kilometers apart, you can observe the corona continuously as the shadow moves, piecing together a comprehensive picture over time. This is what research teams from the US, Europe, and many other countries are planning to do. A coordinated observation network stretching from Greenland to North Africa. High-resolution spectroscopy, measuring the magnetic field directly from light. In recent years, a new technique was developed, measuring the coronal magnetic field directly from the polarized light the corona emits. Previously, we could only model the coronal magnetic field, calculating it based on what we measured at the surface and extrapolating outward. Now, with new generation spectroscopic telescopes, during the 7 minutes of the 2026 eclipse, we can photograph the magnetic field of the corona, seeing directly the structure that normally only exists in computer models. The coronal acoustic wave experiment. Another fascinating line of research, using the eclipse to observe acoustic waves in the corona. Pressure oscillations propagating through the plasma, carrying information about the internal structure of this atmospheric layer. Just as seismologists use seismic waves to study the interior of the Earth, astronomers want to use plasma acoustic waves to understand the interior of the corona. And strangely enough, a total solar eclipse, with the ideal observation environment it creates, is the best time to conduct those observations. There is a logical question you might be thinking of. With all our modern technology, satellites, spacecraft, space telescopes, why do we still need eclipses? Why is a random natural phenomenon still more important than what humans can build? The answer lies in something very simple: scattered light. When you look at the daytime sky, even in high mountains, even with the best telescopes, the Earth's atmosphere always scatters a certain amount of sunlight across the sky, as if you are trying to observe a candle in a room with blazing ceiling lights. Even if you shield it with your hand or a screen, the light of the room still dims the candle. The coronagraph, the artificial solar shield, deals with the direct light from the sun's surface, but it does not deal with the scattered light from the atmosphere. When a total eclipse happens, the moon does not just cover the sun. It covers a large enough area of the sky to almost completely neutralize that source of scattered light within the shadow corridor. The result is contrast between the corona and the surrounding sky that is better than any artificial coronagraph ever built, by a factor of 10 to 100 times. That is why, after more than 150 years of building increasingly sophisticated coronagraphs, astronomers still pack their bags and chase the moon's shadow around the world. Because nothing artificial can do it better. There is a special community in the world of science and astronomy enthusiasts. They are called eclipse chasers. They are scientists, photographers, and people who are simply mesmerized by that moment. Flying anywhere in the world, whether it is the middle of the Sahara Desert or the deck of a ship in the middle of the Pacific Ocean, just to stand in the darkness for a few minutes. Many of them have chased dozens of eclipses. And they all say the same thing. That no matter how many pictures you have seen beforehand, how many videos, how many descriptions you have read, the actual moment still makes you cry. Not because it is beautiful, though it is indescribably beautiful, but because your body knows that something unnatural is happening. The temperature drops suddenly, sometimes up to 10 degrees Celsius in just a few minutes. The wind changes direction. Animals panic or fall completely silent. And your brain, programmed by millions of years of evolution to recognize danger when daylight suddenly turns off, triggers a primal, deep-seated warning signal that cannot be extinguished by reason. Something very large is happening. Something beyond human control. And then you look up, and you see the solar corona. Before we get to 2026, let us pause for a moment to look back. Because eclipses are not just beautiful moments. They have changed the history of science multiple times. The year 1868, a total solar eclipse in India and Southeast Asia. French astronomer Pierre Janssen observed the spectrum of the corona and discovered the mysterious yellow line we talked about, leading to the discovery of the element helium 27 years before it was found on Earth. The year 1919, a total solar eclipse in Brazil and West Africa. Astronomer Arthur Eddington measured the position of stars near the edge of the Sun during the eclipse, and discovered that the light from those stars was bent as it passed near the Sun. Exactly as predicted by Albert Einstein's general theory of relativity. That was the first time relativity was confirmed by experiment. And the very next day, Einstein's name appeared on the front page of every major newspaper in the world. All thanks to a few minutes of darkness. The year 1973, a total solar eclipse in Africa. A team of scientists flew on a Concorde supersonic jet along the shadow corridor to extend their observation time from 7 minutes to 74 minutes. This is one of the most creative experiments in the history of astronomy. And it provided unprecedented coronal data on alpha-fan waves and magnetic structures. And now, in 2026, we have tools more powerful than the Concorde. Sensors millions of times more sensitive. And deeper questions to ask. What will be discovered this time? And this is what I want to say to you directly. The 2026 eclipse is not just for scientists. If you have the chance, if life allows, if the stars align, go there. Spain in August. Blue skies. Major cities along the corridor of darkness. You do not need a telescope. You do not need special equipment other than specialized eclipse glasses to look safely during the partial phase. And then taking them off completely during the sacred seconds of totality. You just need to be there. And let your body feel what our ancestors felt. The awe, the smallness, and the miracle of existing on a small planet, orbiting an average star, in a quiet corner of an ordinary galaxy. But being in the right place at the right time to see one of the most beautiful sights the universe gifts us. The darkness will come. It does not ask for your permission. It does not wait. It just sweeps past for a few brief minutes and then disappears. The only question is, will you be standing in it? And after the darkness passes, when the light returns, when the birds sing again, when the warmth gradually comes back, scientists will quietly sit down by their equipment and begin to read what the solar corona has told them. We will explore that together in the next part. There are things in this world that you cannot map in the usual way. You cannot map a moving storm with a single photograph. You cannot map a rushing river with a static line. And you cannot map the sun's corona using everyday satellite images. Because the corona never stands still. It writhes, it erupts, it changes shape every single second. Filaments millions of kilometers long drift and disappear. Plasma loops form and shatter. Complex magnetic structures appear and reconnect in the blink of an eye. To truly understand the corona, not just observe it, but understand it, you need to do something no one has completely done before. You need to draw a three-dimensional map of it. Not just the surface, not just a cross-section, but the entire structure, every layer, every region, every magnetic field line, along with the temperature, density, and speed of the plasma at every single point. And the 2026 eclipse, combined with data from the Parker Solar Probe and the Solar Orbiter flying through space, is the best opportunity we have ever had to do just that. We have mentioned it from the beginning. And now it is time we face it directly. Why is the corona hundreds, thousands of times hotter than the surface of the sun? This is not merely an academic question. This is not a question whose answer only matters to a few dozen astrophysicists sitting in a lab. The answer to this question will change how we understand all the stars in the universe. Because the sun is not the only star with a corona. Most stars, especially sun-like stars, possess a similarly unusually hot outer atmosphere. If we understand the heating mechanism of the sun's corona, our closest and most easily observed star, we will understand a physical process occurring on billions of other stars in the galaxy. So where are we currently on that journey? Let me tell you about the two leading candidates, and why the 2026 eclipse might help us determine the winner. In 1942, Swedish physicist Hannes Alfvén predicted the existence of a special kind of wave. Waves that could propagate along magnetic field lines within a plasma. Not normal sound waves, not normal electromagnetic waves, but a hybrid wave, both mechanical and magnetic, where the plasma oscillates perpendicular to the direction of the magnetic field. Like ripples running along a taut string. He called them Alfvén waves. And his idea was this. At the surface of the sun, where plasma boils and convects constantly, those chaotic movements create vibrations in the magnetic field lines, like shaking one end of a heavy rope. Those vibrations travel upwards along the magnetic field lines into the corona. And when they reach the corona, where the plasma density is much lower, their energy is released, generating heat. Like ocean waves crashing onto the shore. The energy accumulated over a long journey is suddenly released when it hits a solid bank. Hannes Alfvén was awarded the Nobel Prize in Physics in 1970 for this work. And in recent years, especially since the Parker Solar Probe discovered switchbacks and incredibly powerful Alfvén waves right inside the corona, this theory is receiving more support than ever before. But one question remains unanswered. Do Alfvén waves carry enough energy? And more importantly, what mechanism causes that wave energy to convert into plasma heat? This is what astronomers hope to observe directly during the 2026 eclipse. By tracking the movement of plasma in the corona with unprecedented resolution, searching for the traces of Alfvén waves transferring their energy. The proponent of the second theory is the American astrophysicist Eugene Parker, the same man who discovered the solar wind we mentioned earlier. He proposed that the coronal heating problem does not have a single massive and obvious mechanism. Instead, it is the result of millions of tiny explosions. So small, they cannot be observed directly by any existing telescope. Occurring continuously, relentlessly, everywhere throughout the corona. He called them nanoflares. Because each explosion is about 1 billion times smaller than a regular solar flare. Imagine a beach. Instead of one giant wave crashing onto the shore, you have millions of tiny grains of sand falling continuously. Each grain creating a negligible amount of heat. But added together, millions of grains of sand, millions of tiny explosions, constantly and without end. They generate enough heat to maintain the 1,000,000-degree temperature of the corona. The nanoflare theory is very compelling because it explains certain observations that Alfvén waves do not explain well. Especially the uneven temperature distribution in the corona, with extremely hot regions concentrated at the most tightly twisted magnetic field lines. But the problem is, how do you prove the existence of something you cannot see? This is one of the greatest challenges in modern astrophysics. And the 2026 eclipse, with its ability to observe the corona at the highest contrast and resolution ever, offers a chance to indirectly detect the signatures of nanoflares through microscopic fluctuations in temperature and density within the coronal plasma. But basic science is not the only goal. There is a practical application, an application that governments, major tech companies, and space agencies are investing billions of dollars into: space weather forecasting. Just like we forecast the weather on Earth, knowing a day or a week in advance that a hurricane will hit or a flood will rise. We want to forecast space weather, knowing in advance that a massive CME is on its way to Earth, knowing exactly how strong it is, knowing how it will impact our magnetosphere, so that we can take action. Temporarily shutting down power in the most vulnerable regions before the storm hits, instead of letting the power grid collapse uncontrollably. Putting satellites into safe mode, instead of letting them be permanently damaged. Warning airlines to reroute flights, avoiding high radiation zones in the upper atmosphere. Alerting the crew on the International Space Station, giving them time to move to better radiation-shielded areas. Currently, our ability to forecast space weather is quite limited. We can detect a CME when it leaves the Sun, and we have about 1 to 3 days to prepare. But we still cannot accurately predict a CME before it happens. The reason is because we do not understand enough about the coronal magnetic field, where CMEs are born. If we could accurately map the coronal magnetic field, knowing exactly which regions are accumulating energy, which magnetic lines are being twisted to their limits, we could predict a CME hours, even days before it occurs. And the data from the 2026 eclipse, the most detailed map of the coronal magnetic field to date, is a crucial step in that journey. But perhaps the most exciting thing about an eclipse is not what we hope to find. It is what we do not expect to find. The history of science is full of such moments. When Galileo pointed his telescope at the sky in 1610, he hoped to see the stars more clearly. He did not expect to see 4 moons orbiting Jupiter, the first proof that not everything revolves around the Earth. When astronomers observed the 1868 eclipse and saw the mysterious yellow line in the spectrum, they did not expect that they had just discovered a new chemical element. When Eddington measured the bending of light during the 1919 eclipse, he hoped to confirm a theory. But that result changed the entire foundation of physics. And in every eclipse, with newer tools, with more refined questions, there is always something unpredictable that appears in the data. A strange structure that does not fit any model. An unusual temperature zone that no one can explain. A movement of plasma that goes against everything we thought was true. And it is precisely those unexpected things, those tiny anomalies buried in the data, that are often the starting points of the greatest scientific revolutions. And now let me tell you the final thing in this part. Something that, once you hear it, will change the way you look up at the sky every morning. Every atom in your body, every carbon atom in your DNA, every iron atom in your hemoglobin, every calcium atom in your bones, was forged in the core of a star. Not our sun. The sun is too small to synthesize those heavy elements. But stars that died long before our solar system was formed. Giant stars that burned brilliantly for millions of years, and then exploded in supernovas, blasting all those heavy elements out into space. And from that cloud of matter, from the ashes of those dead stars, our solar system formed. The sun formed. The earth formed. And finally, you formed. You are made of star stuff. That is not a metaphor. It is not poetry. That is chemistry. That is astrophysics. That is the truth. And the sun, the star we are studying, the solar corona we are hoping to understand better during the 2026 eclipse, is our closest relative in the universe. A living relative. Burning, boiling, blasting wind and plasma into space, right next door to us. And we still do not fully understand it. So when the shadow of the 2026 eclipse passes, when scientists return to their labs with hard drives full of data, what will happen? The analysis will take months. Scientific papers will be written and peer-reviewed. Debates will erupt in conferences. Models will be updated, modified, and sometimes completely overturned. And step by step, slowly, patiently, never perfectly, we will get a little closer to the answer. Not the final answer. Science never has a final answer. Every answer only opens up deeper, more fascinating, and more beautiful questions. Like one layer revealing the next. Like the solar corona hidden behind the blinding light of the photosphere. Like mystery hiding behind mystery, endless, bottomless, waiting for those patient enough and curious enough to keep asking. Can you feel it? That feeling of standing before a door, knowing that behind it lie countless other doors. That is the feeling of science. That is the feeling of an inexhaustible curiosity. And that is the feeling that the sun, a star 50 million years older than our Earth, continues to give us every single day. If only we take the time to look up. And in the final part, we will pause. Not to look for more answers, but to sit quietly with everything we have learned tonight. And fully feel the miracle of existing in a universe this profoundly beautiful. We have traveled very far tonight. From the surface of the sun, where plasma boils at thousands of degrees and magnetic field lines are twisted to their breaking points. To the corona, the mysterious atmosphere hundreds of thousands of times hotter than the surface, where giant filaments writhe like cosmic serpents, where the greatest physical mysteries of our century are still waiting for answers. To the solar wind, the invisible current blowing right through you at this very moment, connecting you to the brightest star in the sky in the most literal sense of the word. To the 2026 eclipse, the moment when darkness will fall in the middle of the day and the solar corona will reveal itself in all its magnificence. And to the greatest questions, the questions humanity is patiently, persistently, step by step moving closer to answering. Now, breathe. Set all of those things down for a moment. And just feel. There is a paradox at the heart of the story we told tonight. We can only see the solar corona, the most beautiful, most mysterious, and most important thing surrounding the sun, when the sun's light is hidden. Only in the darkness does the true beauty reveal itself. And I want you to sit with that for a moment. Because this is not just an astronomical truth. This is a truth about life. There are things in life that only become clear when everything noisy, blinding, and rushed around you temporarily settles down. The truly important connections. The things you truly love. The questions you truly want to find the answers to. They are always there, like the corona always surrounds the sun, but they are drowned out and obscured by the blinding light of everyday life. And sometimes, just sometimes, a moment of darkness is needed, so that we can see more clearly. Our sun, judged by cosmic standards, is a completely ordinary star. Not the largest, not the brightest, not the oldest, not the youngest. Just one of about 200 billion stars in our Milky Way, a yellow average-sized star, located in an unremarkable spiral arm of an ordinary galaxy. But, to us, tiny creatures living on a small rock orbiting it, it is everything. Every photon of light shining through your window this morning. Every calorie of energy in the meal you ate today, whether vegetable or meat, originates from sunlight transformed through the food chain. Every breeze you feel on your skin is created by the temperature differences the sun creates on the Earth's surface. Every ocean current, every water cycle, every changing season, and even the fossil fuels, oil, coal, natural gas, upon which our industrial civilization is built, are sunlight stored by living organisms from millions, hundreds of millions of years ago. We are burning ancient light. We are living on the energy of a star. And we often forget that. The people who lived thousands of years ago without telescopes, without astrophysics, without equations describing plasma and magnetic fields, they knew something that we sometimes forget. They knew the sun was not something to be taken for granted. They welcomed it every morning. They thanked it every afternoon. They were terrified when it disappeared, even for a few minutes during an eclipse. And that fear, even though it stemmed from a lack of understanding, held within it a profound truth. That the presence of the sun is not a given. That the light, the thing we turn on every night with the flick of a switch, the thing we look at on our phone screens at midnight, originates from a miraculous physical process happening 150 million kilometers away. From nuclear fusion reactions in the sun's core, where hydrogen is squeezed so tightly it fuses into helium and releases energy, to the moment that light touches your eye takes about 100,000 years. Because the light born in the sun's core does not travel straight out. It is absorbed and re-emitted billions upon billions of times in the dense radiative zone, wandering in a random walk that lasts hundreds of thousands of years, before finally escaping the surface and shooting straight into space. And then it takes only 8 minutes to reach the Earth. The light you receive every day is light born from a time when humans did not yet exist. We live in a strange era. An era where we can know too many things, but feel too little. We know the sun is 150 million kilometers away. But we no longer stop to feel its warmth on our skin every morning. We know auroras are solar wind particles colliding with the atmosphere. But we no longer look up at the night sky long enough to marvel at it. We know the sun's corona is millions of degrees hot. But we go through each day without realizing that a star is breathing and boiling right next to us. Perhaps, and this is just my thought, you may agree or not, perhaps what science truly gives us is not just knowledge, but awe in the face of the beauty of the things that exist. Awe not out of fear, but awe from knowing you are standing before something greater than yourself. Something that has existed for billions of years before you were born, and will continue to exist for billions of years after you are gone. And in that brief span of time, your lifetime, you are allowed to see it. Allowed to be curious about it. Allowed to love it. That is the strangest privilege the universe grants to a conscious being. In the year 2026, on August 12th, somewhere on the narrow strip of land running from Greenland through Spain to North Africa, darkness will fall. And in those few brief minutes when the temperature drops, when the birds fall silent, when the stars appear in the middle of the day, the solar corona will reveal itself. Silvery white, shimmering, ethereal, as it has revealed itself in every eclipse since the Earth was formed. As it surrounded the sun for billions of years before the first human looked up. As it will continue to exist for billions of years after we have returned to the cosmos. And in that moment, whether you are standing in the corridor of darkness or not, I want you to know that you have seen it. Not with your eyes, but with your imagination, through the images that language has painted in your mind tonight, through the understanding that science across generations has accumulated and passed down to us. And in a way, I believe that is just as real. Tonight we have gone on a long journey together. From the solar corona and its million-degree temperature paradox. Through giant plasma filaments and magnetic fields twisted to their limits. Following the invisible solar wind blowing through the entire solar system. To the corridor of darkness of the 2026 eclipse and the mysteries it promises to reveal. And finally, to here, to this moment, as you are lying down, as your breathing becomes steady and slow, as the boundary between wakefulness and sleep begins to fade. Take one final image with you into your sleep. Imagine you are there, on a hill in Spain on an August day, the warm sunlight on your skin, the gentle Mediterranean breeze across your shoulders. And then, slowly, the sky begins to darken. Not completely dark, but a strange kind of darkness, a deep twilight blue like a sunset coming from all directions at once. The stars appear. The air is cooler. And around you, strangers from all over the world standing in silence together, looking up together. No one says a word. Nothing needs to be said. And then you look up, and you see it. The silvery white halo, shimmering, ethereal, unreal, suspended in the sky like a ring of the cosmos. The solar corona. The true face of the sun. A million-degree mystery. A billion-year beauty. And in that moment, you do not think of anything. You just stand there. Small. Present. And grateful. Grateful to be a part of this miraculous universe. Grateful to be curious. Grateful that the darkness sometimes teaches us to see the light. Sleep well. And remember to look up.